Welcome. This is lecture number 2 in our series on basic electrical engineering. In the last lecture, we discussed about voltage, current, power, and energy. There may have been some confusion with regards the statement of EMF. Let me clear that first. We took a mechanical system wherein we had a pump and it was driving. This pump was used to drive, it was pushing water through a tank. You can take a combination of a valve and a tank, fine. So this pump of a mechanical system is analogous to a voltage source driving current I through a resistance R. Now if the circuit is open, voltage is still present there. Even in an open circuit, voltage is available to us. That voltage will still be there, but since the circuit is not complete, it cannot push electrons through the circuit, so therefore current will not flow in the circuit. So in an open circuit, voltage is there, whatever is the amount of voltage, but current will be zero. And we were talking about a mechanical equivalent to this electrical circuit, that is a pump pushing water through a tank. Now I said that voltage is equivalent to a force that pushes current or electrons through this electrical circuit. Voltage in itself is not a force. Voltage is analogous to force. So there is a difference here. When we'll be taking analogous circuits, we'll be seeing that voltage does the same work as force actually does. So pump is pushing water, so it's applying some force. Similarly, we can say voltage is pushing electrons, it is applying some force. In itself, voltage or EMF is not force. It is actually the work done to push this charge across the circuit, but it is taken analogous to force in a mechanical system. So voltage is analogous to force. In itself, it is not force. So get that. So that may have, hopefully that may have cleared some idea. And this, we took a electrical circuit, we took a mechanical system, a pump pushing water through a tank. The tank is filled with water, so it is receiving water from the tank and pushing the water back into the tank through a valve. Now depending upon how this valve is, how much resistance it will offer, whether the valve is closed, whether it is open, or whether it is partially open, or how much partially it is open, depending upon that, the water will have to be pushed at some particular rate into the tank. So that valve can be considered analogous to a resistance here. So it's acting just like a resistance. So more the resistance, lesser will be the current flowing through the circuit. So similarly, if the valve is closed or partially closed, lesser water will be flowing into the tank. And if the valve is completely open, or it is similar to saying that resistance is very small, more current will be flowing through the circuit, more water will be flowing through this pump water system. So this is what we were discussing yesterday, a mechanical equivalent analogous circuit to an electrical circuit. And voltage is not force, it is work done to move a charge, but voltage is analogous to force. It is equivalent to force when compared with the mechanical system. In itself, it's actually work done to move charge. Voltage is work, voltage is not force. So hopefully that may have cleared some doubts. Now moving on, we'll be discussing circuit elements. So in our course we'll be mainly dealing with 5 circuit elements and their subtypes. So these circuit elements are, we have a voltage source, we have a current source. In short, these are actually energy sources. Then we have resistance, inductance, and capacitance. So these are actually the properties: resistance, inductance, and capacitance. The elements are resistor, inductor, and capacitor. So resistor is actually the element physically, inductor and capacitor. So the resistor will be offering resistance, inductor will be offering inductance, capacitor will be having its own capacitance. So these are the 5 elements, and the subtypes we'll be discussing will be mainly focusing around these. The rest of the elements like diodes, switch, MOSFETs, IGBTs, etc. we will not be taking up in this course. So we'll be discussing these 5 circuit elements throughout the course. We'll be using these 5 circuit elements. Now to start with, we have the energy sources. Now we have, first we'll be discussing ideal and practical voltage sources. We have voltage sources and we have current sources. Now these are further divided into ideal voltage sources, practical voltage sources, ideal current source, and a practical current source. And then we have another classification, that is we have dependent sources and independent sources. We'll look at that after this. First, ideal and practical voltage source. So what is a voltage source? We are talking about DC circuits. So first of all, let me get that thing clear. We have DC and we have AC. DC we refer to a system, whether it's DC current or DC voltage, whose magnitude it can be current or it can be voltage, DC current or DC voltage, whose magnitude does not change with respect to time. That's a DC. So DC. And as far as AC goes, AC current or AC voltage is a sinusoidally varying quantity. It's sinusoidally varying, that means it's actually oscillating around the x-axis, around the origin, around 0, fine. So having a peak of plus m and a peak of plus minus m on either side of the scale. It is sinusoidally varying. So these are actually loose definitions of DC and AC quantities. As you actually progress through your degree, you will actually encounter a number of DC and AC voltage. You'll see that DC is not Will therefore have a much more appropriate definition of DC discussed today. We'll say DC is any DC voltage or DC current is any quantity whose average value one whose magnitude is actually not changing with respect to time, and you'll see that the average value of DC will be fixed. Fine. While as far as AC goes, its average value is 0 over full cycle. It has a finite frequency. A DC has has a fixed magnitude, will be constant with respect to time. AC will be sinusoidally varying with respect to time, and its average value will be 0. It will be periodic. Its average value will be 0 over the full cycle, not over the half cycle. Now AC is not necessarily, it will be only sine function. It can be a triangular function also. Fine. It can be square shaped also. So all these quantities are periodic, and their average value over the full cycle is 0, and they are also classified as AC quantities. DC more or less will have a fixed magnitude, but you may encounter a DC like this. So this is a rectified voltage. You might have studied about diode bridge rectifiers, and there you may have encountered such voltage. At the output of the rectifier you will see such voltage. This is a DC voltage. Fine. So there may be voltage which will be sinusoidal, which will be having AC components as well as DC components. So these things will actually AC and DC are much more complex than what they seem, and you will actually learn a lot about these DC and AC as you progress through. But right now you can identify an AC voltage by looking at its average value. If it is equal to 0, it's periodic, it's sinusoidally varying, and it's AC. These all three things should match. And DC can also have an average 0 value if it's having a 0 volt. But DC more or less it will be fixed, and it will have a positive or it can even be negative average value. So that's about AC and DC. Now we are talking about a voltage source. So what is an ideal voltage source? So an ideal voltage source will supply a constant voltage output throughout. Fine. So its voltage will not actually decrease with respect to time, while as practically speaking Practically speaking, voltage does not remain constant, and there will be will not have a constant voltage supply with respect to time. So ideally a voltage source should be able to deliver constant voltage. So if it is if the voltage output of an energy source is 12 volts right now of a battery, so after 1 hour it should also be giving 12 volts. But practically speaking, if it is 12 volts at this point of time, after 1 hour or so it may be as low as 11 volts or 10 volts. So it will actually decrease with time. We have but current can vary in a voltage source. Voltage source actually does not bother with current. Similarly, you will have an ideal current source. A voltage source is shown using this symbol. Fine. So ideal current source. So if your current is constant with respect to time, supplies constant current. Practically speaking again, current will fall, current will dip. Fine. And the symbol for a current source is this. So you have an ideal voltage source supplying constant voltage irrespective of time. You have an ideal current source supplying constant current irrespective of time. A voltage source, the output of voltage source is not going to be constant current. Similarly, the output of an ideal current source is not going to be voltage output of a current source will not be constant. Now, practically speaking, both voltage and current will actually dip with respect to time. There will be a slight dip. More or less, voltage and current will be still constant, but either of the two will not be bothered with current and voltage respectively. So this was one classification of energy sources. Another classification of energy sources is dependent and independent sources. So as far as independent sources go, they are simply the voltage and current sources that we have discussed, whether we talk about ideal voltage source or ideal current source. So this is your voltage source, this is your current source. They are independent, that means they are capable of to function on their own. They are capable to supply energy of their own. They are not dependent upon anything else. So battery is capable of supplying voltage of its own. Fine. So these are independent sources. Then you have dependent sources. They do not have their own energy. Something just like you have moon reflecting the sunlight. In a similar fashion, these dependent sources do not have their own energy, but they are borrowing energy or taking energy from another independent source and capable of delivering energy using that energy source. So accordingly, this will be classified into 4 different sources. You have voltage controlled voltage source. It is represented by this symbol. Fine. You have current controlled voltage source, same symbol. Then you have voltage controlled current source, and you have current controlled current source. What does this mean? If you have a circuit, complete circuit is something like this. You have voltage V here, you have R here, so this is some circuit. Let me draw it on separately. You have a circuit like this. You have, say for example, resistance here, you have another resistance here, you have then a voltage controlled source, you have another voltage controlled source, let me draw resistance here, also resistance. So you have a number of resistances, R1, R2, R3, R4. This is voltage V. Now this one of these voltage sources is voltage controlled voltage source. That means there is a voltage at any point in this circuit, and our voltage source is actually dependent upon that voltage. Now it is not necessary that it will be dependent upon this voltage. Say for example, there is a voltage V1 across this resistance R1. The value of this voltage source can be 3V1. Fine. That means it is dependent upon voltage. So this is voltage dependent. This particular one, this is voltage controlled voltage source. This is current controlled voltage source, voltage controlled current source, current controlled current source. Right. So this particular one is controlled by a voltage. That voltage can be a voltage at any point in the circuit. It is not necessary that it is this main energy source in the circuit. This V1 is itself taking energy from this independent source only. It will, but this voltage dependent source can take energy from any element in the circuit, but it is controlled by a voltage. So therefore this is voltage controlled, and since it will be providing voltage only, therefore it's known as a voltage source. Now let current I2 be flowing through this resistance I. Fine. And I'm saying this is equal to 4I2. 4 is just a constant here, 3 is any constant. Similarly here, it can be any value. It's not necessary. It can simply be equal to 1I2 also. So what does this mean? Now this voltage source is controlled by a current, and that current is actually flowing through this resistance R2. And dependent upon that current, it is able to produce voltage. Therefore this is known as current controlled, but since it is giving us voltage only, so it is a voltage source. So these are both voltage sources but one is voltage controlled and one is current controlled. So voltage controlled, the control of this dependent source is achieved by voltage of any other element in the circuit, not necessarily the independent voltage source in this case. The source, however, V1 will be equal to 0 if V is not present there. अगर independent source वहाँ पे नहीं होगा तो V1 तो आपका 0 होगा ही होगा. But it is not necessary that it is taking directly the voltage from the independent source. It can be controlled by any other element in the circuit, and for this particular example we took voltage control voltage source as dependent on R1 and current controlled voltage source as dependent upon the element R2. So this is what you can this is the example of voltage controlled voltage source and current controlled voltage source. Similarly, this is an example of a dependent current source. Now whether it is voltage controlled or current controlled, that will be dependent upon the value of whatever this is. So say for example this is again equal to 3V1, this is equal to 4I1. So the symbol here says that these are both current sources and they are dependent current sources. Now since this is dependent upon voltage, so this is voltage controlled current source, while as since this is dependent upon I1, this is current controlled current source. So both will be capable of supplying current, constant current. So dependent current sources supply constant current depending upon the value of voltage or current of some other element in the circuit, while as dependent voltage source will be capable of supplying constant voltage, ideally speaking, dependent upon the voltage or current of some another element in this circuit. Fine. So this is ideally speaking. Now practically voltage and current will dip, so they will not be able to supply constant voltage or constant current. There will be a slight dip. So this is the difference between independent sources and dependent sources. Independent sources can produce voltage, can supply voltage, can supply current of their own. Dependent sources do not have their own natural ability to supply voltage or current, but they will be able to provide voltage or current depending upon the voltage or current of some other element in the circuit. Accordingly, they can be classified into VCVS, CCVS, CCVS, or VCVS, CCVS, VCCS, CCCS. Fine. So this is about voltage sources. Now we'll be talking about the elements. Now we have to talk about resistance, inductance, and capacitance. So first of all, resistance. So resistance, what is resistance? It is simply the ability of an element So any element has a capability to oppose the flow of current. So if this opposition is large, that means resistance is very large of such elements. If this resistance is small, then that if this apportion to flow of current is small, then the resistance is small. Fine. So if apportion is very large to the flow of current, such that no current actually flows, they are termed as insulators. If the current still flows in a circuit despite the apportion, they will be then they are conductors, but then how much will be the value of resistance, accordingly they will be off. They can allow the flow of current through such mediums. Fine. Now every element actually has resistance. So practically speaking, theoretically speaking, zero resistance actually refers to a superconductor that actually offers no opposition to the flow of current, and since there will be no opposition to this flow of current, such a source is conducting forever. So what actually happens is that without application of voltage to any conductor, the electrons are actually freely moving in the system, freely moving in the material, and they are not aligned in any particular direction. But as soon as voltage is applied to this particular material, a particular conductor, these electrons are aligned in one direction. Fine. So the negatively charged electrons are actually driven towards the positive terminal of the voltage. So electrons actually flow from the negative terminal to the positive terminals, but we show the direction of current as positive to negative. So once this happens, once the alignment of these materials happens, so in moving in this one direction, they actually collide with one another, and this collision is actually what resistance is. So we'll be taking actually three different we'll be looking at each of these parameters, that is resistance, inductance and capacitance. We'll be having three different viewpoints. One will be the circuit viewpoint, wherein we'll actually try to see how this actually behaves in a circuit. Then we'll be looking at in terms of viewing it as an energy source or energy sink. Fine. So energy viewpoint. And thirdly, we'll be looking at physically, or we can say geometrically speaking, how a resistance actually looks like. So as far as the circuit viewpoint of resistance goes, we can define it through Ohm's law. So as per Ohm's law, we know that R is equal to V by I. Right? So there is a linear relationship between voltage and current. So as you increase the value of voltage, the current will increase, and the graph of this so if we plot V versus I, we'll get a linear relationship, and the slope of this particular line is resistance R. Right? So this is again an ideal perspective where voltage and current actually behave linearly with respect to each other, and the slope of such a curve is given to us as resistance R. But we know with respect to temperature, the resistance changes. Say for example, at temperature T1, resistance is R1. At temperature T2, resistance is R2. Then R2 is equal to R1, 1 plus alpha times T2 minus T1. Alpha here is the temperature coefficient. It can be positive or negative, depends upon the type of material we are using. So some materials have positive temperature coefficient, some materials have negative temperature coefficient. So if a material has positive temperature coefficient, So with the increase in temperature, the resistance of such materials increases. If a material has negative temperature coefficient, then with increase in temperature, the resistance of such materials decreases. So as temperature increases from T1 to T2, normally most of the elements have positive temperature coefficient, resistance of such elements increases. So this is what happens. So if we are supplying voltage to, say for example, some resistance or some bulb which is having a positive temperature coefficient, so as it is on for a longer duration of time, because of the heat loss in the system, the temperature of this material increases. Since temperature is rising, so the resistance of this system will also rise. So initially, if current if say for example a current of 2 amperes was flowing from this bulb, after some hour, after 1 hour or 2 hours of operation, only 0.8 or 0.7 amperes of current will be flowing through this bulb now. So normally speaking, about linear resistors, when we talk about linear resistors, Ohm's law is valid. R is equal to V by I is valid. But most of the times, the relationship between voltage and current may be something like this. It will be non-linear relationship. Ohm's law is still valid because at any point in this circuit, tangential, if we draw a tangent to this curve, the slope at that point will give us R, simply given as V by I. So whether it's a linear circuit or a non-linear element, we can apply Ohm's law to it to derive the value of resistance at that particular point. So as a circuit viewpoint, the resistance is simply the opposition to the flow of current in a circuit, and R will be given using Ohm's law by VR is equal to V by I. Now for our cases, we will not be actually dealing with non-linear systems, we'll be only dealing with linear systems. So for us, R is equal to V by I or V is equal to IR, this equation will hold true. Fine. So this is one perspective of looking at it as a through a circuit viewpoint. Another viewpoint will be the energy viewpoint. Now whether this resistance is a source of energy or whether it's a sink of energy. So resistance will actually be consuming energy, and most of the energy that will be consumed by resistance will be dissipated in the form of heat. So we know that instantaneous power is given by P is equal to V into I. We also know from Ohm's law now V is equal to IR. Fine. So which implies P is equal to I square R. So if P equal to VI is the voltage, so P is equal to VI is the voltage that is generated in this circuit. P is equal to I square R. Same amount of power will be consumed by the resistance, and you can calculate it across the resistance in terms of I square R. So this is actually known as the Joule's law. Now from this we can actually find out the energy. So therefore energy will be given by, from power we can calculate energy by integrating power over a period of time. So I square R, so let's say for example we are integrating it from T1 to T2, so this is dt. So on integration this will be simply equal to R I square T, or in other words R is equal to W by I square T. T here is actually T2 minus T1. T and This is t1 is one time, t2 is another time. So from circuit viewpoint, R is equal to V by I. From energy viewpoint, R is equal to W by I square T. W is energy that is dissipated across the resistance divided by I square T. And thirdly, geometrical viewpoint. So how does a resistance physically, how is it calculated physically? Now again, this fact was discovered by Ohm. So we have seen that, we know that R is equal to rho L by A, where rho is the resistivity resistivity of the material. So different materials will have different resistivities. Now a conductor, now resistivity will not change for a material, but we can change the length of that conductor, we can change the cross sectional area of that conductor, and accordingly we will be able to vary the resistance of that conductor. So we are designing resistance from, if we are designing resistance of our own. So if we take any conductor of any particular resistivity, then we have, if we are designing a particular value of resistance, say for example 10 ohms, then we have to figure out from its length and from its cross sectional area what length we have to choose, what cross sectional we have to choose, cross sectional area we have to choose, so that resistance of this material will be equal to whatever we actually want to design. So in case of electrical machines, where we actually where we actually wind, or different types of machines we have, like transformers, motors, generators. So we wind a lot of copper over the core of the transformer, or the stator or the rotor or the motor. Fine. So you'll actually see there, while designing, we have to design for a particular resistance value. So how much copper, how many turns of copper, what should be the cross sectional area of that copper, what should be the length of that copper, we have to keep it in mind while designing that particular material. So this is about resistance. About inductance and capacitance we'll be dealing in the next session. So resistance from a circuit viewpoint, it's simply the portion to the flow of current in a circuit, defined by Ohm's law as R equal to V by I. From the energy viewpoint, resistance is actually a sink of energy. It actually dissipates energy in the form of heat, that power that is actually dissipated across resistance is equal to I square R. And if we want to find out it in terms of energy, R will be equal to W divided by I square T, where T is the time of dissipation. And from a geometrical viewpoint, R is equal to rho L by A. Rho is the resistivity of that particular material, L is the length of the conductor, and A is the cross sectional area of the conductor. So depending upon L and A for a particular material, we can design a particular resistance value. So resistance is actually the simplest of the three parameters to understand. It has a linear relationship between V and I, and it is quite it's actually naturally present in each and every system. So we'll talk about inductance and capacitance in the next session.